to be in week 9, so it's going to include absorption, but I think usually for absorption it's just up to the tray tower. The pack tower will be included in the final exam. Okay, so anyhow, okay, today let's continue with this. I usually will every semester or every batch, what I try to do is for you to do the example with me in class. Okay, so as for this one, because if you want to do it in class, then it's gonna be taking quite some time. So any of you who's with laptop now, can you go to your CI? Do you have your CI with you? Okay, can you go to your CI and see now in week, this is week 6, right? What should we cover in week 6? Can you go and see? Because I don't want to open this. I don't want to get out of PowerPoint. And I'm gonna like just see. So anyone who has opened the CI, what can you see in week 6? What should have what should we be finished with? With which topic is it?
Yes, it's separation process.
I know it's separation, but should we? It's absorption for week 6. Distillation should start in which week?
Distillation. It's week 7.
Week 7, Doctor.
Oh, week 7. So it should be next week. So I'm really worried if I do not finish this today, then we will be delaying our distillation. Distillation is a very long topic for us to cover. Okay, so let's just start with this one. For example, 10.63. Actually, you can read the question yourself, but the case is you have a tray tower like this, okay, and you want to separate ethyl alcohol from the gas stream. Okay, so you have 100 kilomole per hour coming in here, and this flow is containing 2.2% mole of alcohol. Okay, here, can you see my cursor? Okay, so here is the inlet of your gas flow, and this is the inlet of your solvent. So this solvent in this case is it's 100 kilomole per hour as well. Is it? Oh no, L naught is not there. L naught is given as a minimum liquid flow rate, as a factor of the minimum liquid flow rate. So do you remember during cooling tower or humidification, you have minimum gas rate, right? Yes?
Yes.
Yes.
Okay, so you have minimum gas rate. Now in this absorption topic, you have minimum liquid flow rate. Okay, so your actual L naught is actually as a factor of the minimum liquid flow rate. So in this kind of question, you have to find the minimum liquid flow rate first, and then only you can find your L naught. Then only you can proceed with all the other or the rest of the calculation. Okay, so as usual for a tray tower, you have to determine the number of trays needed, and you have to do this graphically and as well as the analytical or analytical method, okay, using the equations. Okay, so the only condition given to you is this: it is desired to recover 90% of the alcohol. Means that you have to calculate how much alcohol you have in the beginning here, and you have to recover 90% of this, which means that the 90% from this stream will come out at the outlet of the liquid, okay, or the liquid outlet or the solvent outlet. Now the 90% of the alcohol here will be transferred to that line, and what's left here is only 10% of the alcohol. All right, and you have an equilibrium relationship with y equals to mx with the gradient to be 0.68 of x. Okay, so I hope you still remember, because you have done your example and you already did some exercises at the back of the book. I've given you some assignments, and then this is how you draw it, and you write down all the information you have with the recovery of the alcohol, and this is your equilibrium line, and then you have to calculate or determine the number of trays. And first you want to know all the flow rates and also the composition. So this is very important. You have to be able to calculate all the unknowns here in the diagram. So you want to know what is your XAN, what is your V1, what is your YA1, and also your LN. Okay, so the way you calculate that is using the condition given to you, where you want to remove 90% of the alcohol in the initial gas flow. All right, so this is V prime. Do you still remember what V prime is? Someone? What is V prime? What is L prime?
Inert gas and inert liquid.
Okay,
That means
so
they don't have the A. The A.
Yeah, thank you very much. Okay, so V prime is actually the inert gas, and L prime is going to be your inert liquid. And the way to calculate this, I have already shown you how, right? So then you can calculate V prime as 97.8 kilomole per hour, and you can also calculate the flow rate of the alcohol alone, and it's going to be 2.2 kilomole per hour. And you remove 90% of the 2.2 kilomole, which is 1.98, and this is going to go into Ln, and the balance of the alcohol, which is 0.22 kilomole per hour, will go into V1. Okay, and then your V1 is actually the V prime, which is the inert gas plus the alcohol that is left as a balance here, and then this is the total flow rate of V1. And when you want to calculate the composition or the concentration of YA1 over there, you just take the 0.22, which is the alcohol, over the total flow rate, which is the inert plus the alcohol. Okay, so all right, so in order for you to calculate to determine the number of stages, you have to find the L mean first. Okay, the way you want to start this is, first you have to draw your equilibrium line. So using this equation, straight line equation, you have to draw the equilibrium line, this one, okay, the equilibrium line. And for you to get the L mean, you have to start with the point over here. So the point over here is plotting YA1 against XA0. So your XA0 is supposed to be 0, right? And your YA1 is what you get from this calculation, and you can get your first point for your operating line. And then you have to connect that point to the point P, okay, and draw the straight line. And this way, this actually your XAN max, not XAN, is XAN max, and this one is your YN plus 1A. Here is YAN plus 1. So YAN plus 1, which is already given by the question, is 0.022. Okay, you take 0.022, you go horizontally where it meets the equilibrium line, and then you go down here. You will be able to calculate your XAN max. Okay, who's confused now? How to get point P? Who's already confused or already mixed up and lost it already? Anyone? Or are you all okay? Okay?
Okay, doctor.
Okay, doctor.
Okay, so first you have to find the point P, which is according to the value of y(a(n) plus 1 that is given in the question, and you can find your x(a)n) max, okay, which is from the graph is 0.03235. Then you proceed with the calculation of your L min, where you put the value of XAN max here. Okay, this is the general equation of the operating line. And then you put your value of L, this is unknown, L prime min. This is what you want to calculate. You know your V prime and you know all the other values. What you don't know here is only L min, okay, because this x at the point of a and max, your L will be the minimum, which is L prime minimum. So this is what you want to calculate, which is, if you do the calculation yourself, then you will get L prime min as 59.24 kilomole per hour. And then only you can calculate your L naught as a factor of the L min, which is already given to you as 1.5 times the value that you get from this calculation, and you finally get your L naught. And then from your L naught, this is your L naught, and for your Ln, you can calculate from the mass balance you do, okay? This Ln is supposed to be what? Apa tambah apa? What plus what? 88.86 plus 1.98 ni apa? What is it actually? Anyone?
The 90% of alcohol.
90% of alcohol plus
With the inert water.
with the initial or the inert, right? The inert H2O that comes. Okay, thank you. I'm actually trying to configure my WebEx so that I can see you guys, but it's very hard and I couldn't see because when I enter PowerPoint, it becomes full screen and I can't see anyone. Okay, so I don't know who's answering. I don't know what your name is and I don't know who's speaking. Okay, so you can okay, it's quite hard, but it's okay, you will just continue. All right, so now you get your, where were we here? L naught, you get your Ln, and then you put everything into your operating line, and finally you will be able to calculate your XAN, okay, instead of your XAN max just now. This is your real XAN, okay. So once you get those 2 points, okay, tadi you start with XA naught. Now you have the XAN already calculated, and you already have your YA1 as well as your YAN plus 1. Sorry, these symbols are all mixed up and not the same as or not synchronous and not homogeneous throughout the slides. Okay, so I hope you're not confused. It's just the same thing. Okay, so now you got 2 points already. The first point is there and the next point is there, and then you just connect those 2 points and you can start your stepping off the graph to calculate the number of stages by stepping off from the bottom here. So this is 1 tray, 2, 3, and 4. And in this case, miraculously or coincidentally, the number of trays is on the dot, 4 on the dot, not 4 point something or something like that. Okay, so in this case, the number of theoretical trays calculated by or determined by the graphical method is 4. And then as the question asks you, you have to do both using the graphical method as well as the analytical or numerical method. This is the equation that you should use, and all the information you have from this M is from the straight line or the gradient you have from your equilibrium equation. Okay, and for A, you will calculate your A1 and AN based on this equation. Okay, and all these can be calculated, and once you have all these values, then you will just put into your equation over here at the top, and then finally, you will put all the known numbers, the known values into the equation of n, and you will get 4.04. So, rightfully, what you should get from the calculation or from the graphical method, you should get the same number of theoretical traits. If they are different, then you have done something wrong somewhere, and you have to trace down where you go wrong, and you have to see that which one is actually the right one. Okay, so rightfully it should be the same. They should be the same. Okay. All right, so those are all for trade tower. Okay, so now we are coming into a different, kind of different. Okay, tadi trade tower, now we are coming into pack tower. This pack tower is actually something quite similar to what we did in the first topic. Okay, the mass transfer topic. All right, so or the cooling tower as well. The cooling tower also is using a pack tower, and this is how it looks. Okay, so you can Google all this in the internet. Okay, you can find all this sort of different packing style. You sometimes have loose packing like this, loose and random packing, or you will be using structured packing like this. This is like a block of packing with some patterns of solids in here, and when you want to remove it, it should be removed as a block of packing. Like this, it's a loose and random packing, and this loose and random packing, you will have a lot of many types of packing available in the industry. There is ratchet ring, there is interlock saddle, there is bull saddle. Okay, those are all previously invented by previous scientists, and they have all done their research, and they have come up with the specific friction and the specific surface area for all the shapes of the packing. Okay, so this is how structured packing looks like, and this is a packing support for the loose and random packing. And you will be seeing all this if you really work in a chemical plant in the future when you have graduated. Okay, so unfortunately in Malaysia, usually engineers are all gonna only run the plant. Okay, it's very rare that you got to design, but actually the engineers should know the theory or the knowledge to design a pack tower or whatever unit operation that is involved in the chemical plant. Okay, so the first important point that you have to look at in a pack tower is the pressure drop and flooding in pack towers. Okay, so good job. Okay. So what is first is loading point. You have to know all these kinds of what do you call it, terms in a pack tower. Okay, loading point is actually the point where the gas starts to hinder liquid from going down. Okay, so we will get local accumulation of liquid starting to appear in the packing. Okay, so you don't want this to happen. This is not ideal for a pack tower. A loading point, when you reach a loading point, this is not good. Okay, so after you have reached a loading point, if you still do not see and if you still do not troubleshoot the problem that you face in your pack tower, you will be facing flooding point. Okay, flooding point is a point where the liquid no longer flow downward, and it cannot flow because your velocity of flow rate of the gas going upward is too high, and your liquid will be blown out by the gas. All right, So you don't want that to happen, and flooding point is quite dangerous because some explosion can happen, and the buildup of pressure is gonna be making it dangerous for the plant. Okay, so you don't want flooding point to be occurring in your plant. And in the actual operation or normal and favorable operation, the gas velocity should be well below the flooding point, and the optimum economic gas velocity is usually half or more of the flooding velocity. So for each pack tower that you design, you have to know where is the flooding point or the flooding velocity, and then what they should run with the pack tower is they have to operate at half or more of the flooding velocity. Okay, so there is also a graph or a correlation for you to calculate the pressure drop in random packing, because this pressure drop will give you some indication of the flooding point, the loading point. Okay, so you have to be able to calculate the pressure drop in your packing. So this is actually the graph that is correlating between the capacity parameter and also the flow parameter. So if you see, the capacity parameter is actually an equation involving superficial gas velocity and also the densities of the gas and liquid. And as for here, you have the flow rates of the liquid and the gas, also the density. Okay, so with all this, you have also here the FP, which is the packing factor. So FP is going to depend on which type of packing you use, and V is actually the kinematic viscosity. So you have to really be careful because there's two quite similar symbols here. This is Roman V. This is the normal V. So the normal V should be viscosity, or sometimes it's called mu. Okay, and then this is mu over rho L. Okay, and over 62.4. This is how you calculate this, and this is superficial gas velocity. Okay, and those are all the gas flow rates, and accuracy of this graph is actually plus minus 11%. So if you have your capacity parameter, you have your flow parameter calculated, then you can point out what is the delta P or the pressure drop according to these correlation. Okay, so the way for you to calculate or to predict the limiting pressure drop at flooding, this is the equation that you will use. Okay, this will be according to the friction or to the packing factor FP, and this is the pressure drop that you should get for flooding. Okay, and this is the pressure drop that you have to avoid. Okay, and then the value of the packing factor is from 9 to 60, and if it's within this range of 9 to 60, the accuracy is plus minus 10 to 15%. If your packing factor is 60 or higher, you don't even have to use that correlation anymore. You can just straight away use this value. Okay, so there's actually a procedure of calculating the delta P, and also to calculate all the parameter capacity, and also the other capacity, what do you call it? The x-axis. Okay, then I'm not going to cover this. You can read this in the book. Okay, there's an example even for this part of the chapter. Okay, so now we'll go to straight to the core of the calculation for pack tower. Okay, so as you see, what you use for a tray tower, you draw it horizontally, right? But for a pack tower, you cannot draw it horizontally because it's a packing. Okay, it's a packing and it's gonna be vertical. Actually, the tray tower is also vertical. Wrong if you want to draw it vertically, and just to save some space, maybe they are drawing it horizontally and just to show you the flow. All right, so for a pack tower, this is how it looks like. You will have the gas flowing upwards, and you have the liquid flowing downwards. And if you notice, the symbols or the numberings are all different from the tray tower now. So don't get confused. You have to take note of this, because what you have in the tray tower, the solvent flow rate is called L0, kan? But this time it's called L2. So you have to be careful with that. And the outlet is called L1, but in the tray tower it's called LN, right? So it's quite different over there, and this is more or less like the cooling tower, right? The numbering is like the cooling tower. So this is V1, which is the gas flow rate that's coming in, and the gas or the outlet gas coming out here is V2. And V and Y, L and X without the numbers are actually at any point of your packing. Okay, so we are going to use the same operating line. Okay, the same operating line. Okay, so this is the balance on A for the overall boundary, which is from the inlet to the outlet. So that's how let me draw the boundary over here. So this one, okay, this one, oops, scribble, okay. So equation is actually the boundary is here. Okay, so that's for the overall boundary, and as for this one, this is the boundary. So this is actually taking that equation, and the X and Y is actually at any point of the packing. Okay, so you have absorption and stripping like this. Okay, and as for absorption, you will have your equilibrium line over there and your operating line on top. Equilibrium line, and for stripping it's the other way around, where you get your operating line below your equilibrium line. Okay, so first, you will have to calculate this, which is the limiting and optimum L over V ratios. So when you have to calculate this, what you have to do is something similar to the tray tower. Okay, so you have to use that equation, and you have to get this point, okay, from the condition given, and then you plot that point P, and this point P actually is from Y1. Okay, so from Y1, yeah, you have your equilibrium line, right? So this Y1, you could just go horizontally, and when it meets the equilibrium line, you just bring the line down, and you will be able to calculate or to read your X1 max. From this X1 max, you will put this into the equation for you to calculate the X1. Okay, you will put that number into that equation. So this is just as what you have done for the tray tower, right? So you put in your L min, you put, no, you have to calculate your L min, you put in your X1 max, okay? Put in your X1 max, these are all known values, and then you will be able to calculate your L min and L min. Okay, so that's how you have to get your L minimum first. All right, so then you will be using all these equations, okay, to calculate your the height of the tower. So remember, for a tray tower, you will be asked, or you will be required to determine the number of trays. But for a packed tower, you will be asked to calculate the height. Okay, the height. So the height of a packed tower is called Z, 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 and Z. And you have 4 different equations because you will be using different coefficient. This one is gas mass transfer coefficient, and then this one is liquid film mass transfer coefficient. So for small k, it's film mass transfer coefficient. For the capital K, these are actually the overall mass transfer coefficient. If it's K prime Y, then it's for the gas, and this one is for the liquid. Okay, so when you're using these equation, you will be seeing this impression, which is in this case, this is y minus yim, right? So this will be calculated by that equation. So yang ini will be calculated as that. Okay, and this one will be calculated as this one, and that one will be calculated as that one. All right, so as for V and L, you have to calculate the average value using this equation, which is V1 plus V2 plus, divided by 2. And if it's for the liquid, then you take all the liquid values. And remember, this is in the case where the equilibrium line and the operating line are both straight lines. Then only you can use all these equations. Okay, and this is followed by a case where only your operating line is a straight line, but your equilibrium line is a curve somehow. Okay, so if only your operating line is a straight line, then these are the equations that you have to use. So this now is involving integration. Okay, that integration. Okay, this is somewhat more difficult than the first case where you have both of the lines straight, and these values are actually the same as this. Okay, so you have to calculate that by using all this equation. Macam tu. Okay, but still you have to solve the, what do you call it, the integration, and that's going to be quite challenging. Okay, but unfortunately this is always the final exam question. Okay, so I feel really bad for you guys, but this is what you're going to face in your final exam. You have to do the integration. Okay, so the last case is where, not the last case, there's only 2 cases. Okay, so this is the general procedure that you have to use when you are calculating the Z, which is the height of the tower. First, like I said, you have to plot your equilibrium line and also your operating line, and then you have to try and error by using the first trial as that value. Okay, the slope of the line, the slope, you will see what slope that I mean by this. Okay, and then you have to use values of the yi, xi, or y star, x star is determined by this slope. Okay, so once you get those number of yi, xi, y star, yi is when you use gas film mass transfer. Not only gas film mass transfer, when you use the film mass transfer coefficient, you will get yi, xi. If you use the overall mass transfer coefficient, you will get y star and x star. Okay, so once you get all these values, then you have to calculate the real slope, because the first one is actually just an assumption, or the first trial is not the real one. And then you have to compare the latest value of your yi and xi to the first. Okay, so these are the values that you get for the second trial. You have to compare that to that first trial, and if it's the same and without much variation, you can stop. Okay, so it can be after second trial, it can be after third trial, it can be after fourth trial. So you just have to hang in there and do it until you find the same number between the trials. Okay, so once you get that, you can plot the value of 1 over y minus yi. This is in case where you have to solve the integration. Okay, when you want to solve the integration, then you have to calculate the area under the plot, and you can also choose not to plot and you just do it numerically. And once you get that area under the curve, then you can calculate the height of z. I know that looking at this, you will find it quite difficult for you, right? Because it's not clear how you do. So let's look at one example so that it's going to be not that blur to you. Apa ni? Oh. Okay, so this is stop sharing. Wait, yeah. I want to see you guys actually. Can you see my screen now?
No.
Yes?
No, doctor.
What screen are you seeing now?
Black.
Blank.
Yes.
There's nothing.
Yes.
Itulah, I don't like this webback. Sometimes I lost you guys. So I stopped sharing. What do you see now? You see all of you there, kan? Betul?
Yes.
Yes, doctor.
Yes, doctor.
Okay, sekejap. Alright, so now I'm gonna share again. Who has the book? Can you read the question? Shalini, read the question, please. Can you read the question for us for this example?
Not sure, doctor.
Okay. You can read the example so that your friend can relate to the diagram over here.
Okay, doctor.
Mm-hmm.
Acetone is being absorbed by a water in a packed tower having a cross-sectional area of 0.186 meter cube at 293 K
Mm-hmm.
and 101.32 kilopascal, that is 180.
Mm-hmm.
The inlet air contains 2.6 mole percent acetone and outlet 0.5%. The gas flow is 13.65 kilomole inert air per hour.
Here.
The pure water inlet flow is 45.36 kilomole water per hour.
Over here. Okay.
Flume coefficients for the given flows in the tower are KY equals to 3.78 10 to the power of negative 2 kilomole per second and meter cube.
Mm-hmm.
And then K prime X8 equals to 6.16 10 to the power of negative 2 kilomole per second meter cube mole fraction.
Mm-hmm.
That's all, doctor.
Okay, so what do you have to calculate?
I have to calculate the tower height using K prime YA
Mm-hmm.
and B repeat using K prime XA.
Mm-hmm.
And then the third one will be calculate the capital K, that's overall mass transfer coefficient, K capital K prime, YA, and the tower height.
Okay. So this is a very long. The solution is not. The question is not long, but the solution is gonna be very long because it has all of the variation there. You have to calculate that using the gas film mass transfer coefficient, and to B you have to repeat using the liquid mass transfer coefficient, and then finally you have to calculate with the overall gas mass transfer coefficient, but you're not given with one. Okay, you're not given with that. So wait, oops, you're not given with this is so annoying. Wait, and you're not given with that. Okay, so you have to be able to determine that coefficient. Okay, now let's look at this. Now you have that diagram. Okay, you have to be able to draw this standard diagram, and you have to write all these this known information, the known values on your diagram. And then what you have to do is you have to first start with the material balance. Why do we have to start with the material balance? Who knows? Siapa Zaki? Who's Zaki? It's Mr. Zaki. Where is Mr. Zaki? Mana Zaki? Are you here, Zaki? Mr. Zaki? Tak ada Ke dia tak boleh? Is he not able to? You're not able to turn on your mic, Zaki? Dia buka dekat chat je. Tak boleh How about Umar? Umar, why do you have to start with the mass balance or the material balance? Mr. Umar?
Hello there.
Why do,
Can you repeat the question?
why do you think we have to start with the material balance?
Because the calculation need the mass balance value.
What value?
Um,
What value that you need to know?
the mole percentage.
The
Of
mole
of
percentage.
acetone. Acetone.
Give me the symbol, the name of the stream, the symbol used. Okay, what do you want to find from this diagram? Nampak tak pencil saya tu? Can you see my pencil? Okay, so what do you want to find here in that diagram?
V2.
Okay, you want to find the V2, which is the outlet flow rate of the gas. Okay, then
And then L1.
L1. Okay, it's very quite simple, right? Ke tak simple? Okay, L1. Then you apa lagi that you have to find other than that? Other than V2 and L1?
The S1.
Yeah, the X1, because all
Okay.
other flow rate and composition you are already given with it. right? So you have to do the material balance in order for you to know the flow rates and also the composition that is still unknown, that are still unknown. Okay, so you have to really know how to use this operating line equation for you to be able to calculate all the flow rates and as well as the composition that is unknown. Otherwise, then you are going to be stuck and you don't know where to proceed. Okay, so then what you have to do is after you have calculated all those, you will be able to plot your operating line. Okay, so your equilibrium, how about your equilibrium line? Are you given with any for the equilibrium line? How do you get your equilibrium line? Shuhaib, how?
Using gradient given
I cannot hear you, Shuhaib.
using gradient that given. Hello? Dengar?
Sorry.
The equation.
How tak dengar? How? Sorry.
Using the equation that given in the question.
Okay, what is
Hello,
the
dengar?
equation given by the question? What is the equation given by the
Sekejap.
question line? It's not nice. You don't have the question with you? You don't have the book? You don't have the book.
PDF. I don't have.
Okay. Shalini, you were the one who read the question just now. What's the equation for the equilibrium line? Are you given with a set of data or you're given with a line equation?
Actually, we just use the y equals to mx. That formula, we find the m
Okay.
first.
What is the equation given for the equilibrium
Uh,
line?
y equals
Y
to
equals to
1.186x.
Y equals to what?
Y equals
This
to
line
mx.
is Y equals to
Mx. That's the formula. 1.186x.
1.186x. Right. So this line you should get, or you should produce this line by using the equation or the linear equation given to you. Just put any value of x over here into that equation, then you will be able to get that equilibrium line plotted. Okay, so and then this one are all determined or plotted using the x and y value that you calculated from the mass balance. Okay, then after you have gotten all that, you have to do a trial and error. Okay, the first trial you should use the values that given by the question. Okay, so okay, cuba tengok sini. These values that you're given with. Okay, K prime. Monabir, are you here? I saw him leaving. I saw him left. I saw you left just now. Are you still in the class? Monabir? Tak ada eh? Is he not around? Monabir is not around. Okay. So, but anyway, I have to still deliver to you in English because I think he's gonna be needing to see the video afterwards because he's not in the class today. Okay. I think he scan for attendance and then he leaves. So I don't want you to be doing that, okay? So now I have like 34 participants, including me. So there's only 33 of you. There should be 37 of you in here. So some people are missing the class. I know they maybe have scanned the attendance, but they're not in the class all the way. So I don't want you to be practicing or to practice. I want you to be okay. So because otherwise I know you can see the recording but it's not good. It's not nice for your record. Okay, so let's go back to this. You're given with the coefficient, okay, film mass transfer coefficient over here, and this one is for the gas and this is for the liquid, and you already calculated all this, okay, y1, x1, y2, x2. This is given by the question, which is the cross-sectional area of the column. Okay, then the first step that you have to do is the trial and error from the slope of this. Okay, these are using the values that is given to you in the question. So what you have to put as your slope here is those values. Okay, just put it there, and all these using the value of x and y that you get from the calculated value. Okay, not the initial one, but the value that you calculated to be the outlets. Okay, and then you put there, and you can get the slope to be 1.6. So when you get this slope is 6, what you have to do is you want to find the interface value. So remember what we did in the first mass transfer part of the chapter. I already show you how to plot a line only with having one point and the gradient or the slope, okay? So you have the slope now, okay? And you have to always remember in your head, that the interface values, x, y, or the yi, xi or yi, all these interface values should be produced by the equilibrium line. Okay, ini equilibrium line. This is the equilibrium line. So this is the operating line. Okay, so you have this slope of the line in order for you to plot this point for you to get the interface value. Okay, so you have this point definitely. You have x1 and y1, but you don't have this point of x and y. Okay, so you know what to do. You have the slope. Just take any value of x. This mostly at this point of time, you don't even know what your x is, but you just pick a value for x. Maybe you want to try 0.1, 0.012 maybe, but in this case, in this example, what sort of x is it? Try on. I have to see the next slide. Okay, so for point number 1, okay, what it's taking is sorry, this one. It doesn't show you how. Here, but let's say you take your x to be 0.012. Okay, and then you put the equation of slope. Remember how y1 minus y2 over x1 minus x2, right? So you have here the value of what do you call this? X1 is 0.00648 and the y is 0.026, right? This is the coordinate for that point. And this one, just take any value. Let's say you want to take 0.012 maybe, and then you calculate the corresponding y. Okay, and rightfully you will get somewhere here point. Okay, so this way you take your ruler from that point, and then you just extend the line until it meets the equilibrium line, and you have to do the same for these bottom points. Okay, just do the same, or when you have this slope of negative 1.6, you have that line, and you will be able to read down the interface values. That is your interface value. Okay, you don't have to do this yet. You don't have to do this yet. No, you don't have to do that yet. Okay, so for this first trial, you just have to find the value corresponding, or the interface value corresponding to that, and the interface value corresponding both the xi and yi. So you read down this value, you read also that value, and those values happens to be 0.0154 is the yi. This one 0.154 over here, and this is 0.013 sini, 0.013. Those are the interface values that you get from your first trial. Okay, from that first trial, you get all these interface values. Then you will use this. Okay, let's say you are lost. What you have to remember is for you to ke depan sikit so that you can actually build up what actually you want to find. Okay, so what you want to find actually is to find the z. If you want to find the z, you have to, let's see, you have to use the equation of z. Mana tadi? This is second trial already. I want to show you the equation of z. After this is when your point 2 and point 1 is the same, are the same. Then you go to the equation of z. Okay, those are actually for you to solve for z. And when you're lost, just look at the equation of z here, and then you can determine what you want to do. And in this case, you don't even have to do the integration, because both the equilibrium lines and the operating lines are straight lines, so you just can use this equation straight away. Okay, so that's why you are doing all this, to find the interface values, because you want to proceed with this. Okay, so without the interface values, you cannot proceed with this, and you will not get the actual value. Okay, like for the first value, when you start, okay, you start your trial and error, the first value that you use is not involving the interface value yet, because that's an assumption. Okay, that's an assumption. And then you use that beginning or the initial value for you to be able to calculate the real yi and xi to be put into this log mean equation. Okay, so this 1 minus yi mean is for part, 1 minus xi mean is for the calculation of that part, right? So then, oh, sorry. And then once you get the interface value like this, okay, all these interface values, you will put into this equation like that. Okay, and then when you put those into this equation, you will be able to get the 1 minus yim and 1 minus xim to be these values. Okay, so those values are going to be put into the second trial. Okay, so for the second trial, you have to use the full equation of the slope. Now, not only using the assumed value for the first trial, you use the new value of the 1 minus xim that you calculated from the previous slides, okay, and then you calculate the new slope. And luckily for this second trial, it looks like the slope has first trial, so you are lucky. So this, for this question, for example, the slope stays at 1.6 something. This now for the first trial it was 1.60, and for the second trial it's negative 1.61, and they are more or less the same. So you can conclude with the interface value that you got from the previous trial. Okay, so then you will be using all these values into the equation of z. Okay, and then slope number 2, if you do the slope for the slope at 0.2, this is 0.2, this is 0.1. Okay, because you have seen that you can try as well for slope at point number 2. You can put all the values in, okay, and then you will be able to find that, which is also very near to 1.6 and 1.61, and then you can conclude that those are the values of yi2, xi2, and y star 2 at this end of the graph. Yang tadi tu for this end of the graph. Okay, so once you get all those, you want to put all your known values into this equation. Okay, all these value ni, okay, because for your original equation you still need yi1, yi2, yi1, yi2. This is when you're using the liquid film mass transfer coefficient. Okay, if you're using the gas mass transfer coefficient. If you're using the liquid mass transfer coefficient or the film mass transfer coefficient, you have to find all the x values, not the y value. Not find, you already found all the numbers, all the values are here, but it all depends on which equation you want to use. Okay, so if you're using gas film mass transfer coefficient, you will be using yi1 and yi2. If you're using liquid film mass transfer coefficient, you will be using those values. Okay, and if you're using the overall mass transfer coefficient, then you will be using the star values. Okay, so you put in all the values over here, and then you will get that value of the log mean expression, and the log mean value is there. Okay, so that is actually for which part? For this part. Okay, so y1 and y2 are all from the question. Okay, and for this part, this is what you have found using the equation. So when you put all these known values into the equation of z, you will finally get to calculate the value for z. Okay, and also using all these values of v1 and v2 to calculate the average. Okay, the average value for the flow rate. Okay, so finally you will be able to calculate your z to be 1.911 meters. Okay, susah ke?
Susah juga.
It's quite difficult because you have to do the trial and error part. Kan? You have to do the trial and error part, and it's the first time that you see the equation. You're still not familiar with it. When you do a lot of revision, you do a lot of exercises, then you'll be very familiar with the equation, and it should not be that difficult for you anymore. Okay, so actually, when you use the film mass transfer coefficient for gas or for liquid, and also the overall coefficient, the answer all should be the same. Okay, Z that is calculated should all be the same, no matter which coefficient you use. Okay, so that is how you do, and you have to repeat with kx, right? K prime x, and also k capital K prime y. So that you have to do yourself. Okay, do yourself. I would like you to repeat that and hand in to me. Yeah, hand in to me your calculation of Z using for B and C. For B and C, okay? I want you to hand that in through e-learning. Okay, so we are now at the last part, which is this quite the same as for the humidification. Okay, for humidification, you also have seen this. Okay, which is using the height and number of transfer unit. What you see for the equation of Z, there are 4 variations in the equation of Z, all depending on which mass transfer coefficient that you're using. Okay, so Hg, HL, HOG, HOL are called height of a transfer unit. Okay, so this height of a transfer unit is actually calculated using that expression, or the first part of the equation. Okay, as for your number of transfer units, which is those NOG, NOL, NG, and NL, it's calculated using that part, or the second part of the equation. Okay, so normally you will be using one of these 4 equations, not all. Okay, we are not that mean lah sekejam itu nak suruh you kira. Using all the 4 equations, you will be able, or you will be asked to choose, or not asked to choose, you will be asked to calculate using only one equation or one equation. Maybe gas film mass transfer coefficient, maybe overall gas mass transfer coefficient, is all according to the question. Okay, and this is in the case where both the lines of operating lines and equilibrium lines are straight, and this is when your operating line is straight but your equilibrium line is not straight, and this is going to be more challenging to you. Okay, so you will be able to calculate the number of a transfer unit, which is called NOG. Okay, NOG can also be calculated using this equation. So it's you have to really gather all this information or knowledge, okay, because this NOG, if you see from the last slide, okay, this NG, NL, NOG, NOL is that actually comes from this part of the equation, right? So let me just erase all that. This NG, NOG, NOL, NL all comes from the second part of the equation, okay, accordingly. Okay, but you also have to remember, not only it can come from this, okay, all of this, not only it can come from all this, it can also come from this equation. See, okay, you also can calculate those NOG, NOL using this equation. Okay, so this is when you have this phrase mentioned in the question, which is saying when the major resistance to mass transfer is in gas phase, NOG or NG. This is for absorption. If it's for stripping, then the major resistance to mass transfer is in liquid phase. So you can calculate the NOL or NL should be used for stripping. Okay. All right. So this is the equation for if your operating line is straight, then you can calculate your NOG like that. And if your equilibrium line and operating line, the equilibrium line is straight and not parallel, you can use that for NOG. Okay, so this is for stripping, which is NOL. You will be using that equation. Okay, so remember, okay, not only you can find it from the interface values or the star values, you can also find it from these equations. Okay, as for the HOG and HOL, you have to calculate using the slope of the equilibrium line, and then you can calculate your HOG, your HOL, not calculate, you can relate the HOG and HOL using those equations. Okay, so remember about this. Okay, you cannot just ignore all these points, because sometimes the question not only come in the form of the example that I've shown you. It can also come in other variations, because this is an open book. It can be anything. Okay, so you have to know how to use all these equation, and if you don't have certain information, it might be what do you call it, intentional. They intentionally do not give you the values or the unknowns, because you don't really need it. Okay, because there are certain ways for you to do, and you have to know how to use all these equations. Okay. Alright, so saya nak tengok sampai mana lagi ni, supaya whether you still can grab all these, and or maybe you are already full. Are you still able to absorb all these if I continue? Because I think this is too much already for you guys. Right? Right or not?
Yes, Doctor.
Yes, Doctor.
So you boleh absorb lagi. You still can take more.
Tak boleh dah, Doktor.
Tepu dah. Okay, I also feel like I cannot just like continue and put you in the misery of understanding all this in one session. So, okay, let's recap. Okay, let's recap a little bit. What you learned today is you to know how to calculate the almin. Okay, kita recap sekejap before we end the class. I know you're overloaded already. Siapa ni? Jong Kailun. Okay, yeah, I know that you. I know it's not gonna be useful for you anyway if I still continue. Okay, so let's recap before we end the class. You have learned on how to calculate annual mean today. Okay, L mean, and then followed by calculation or determination of the number of stages. From the L mean, you get the L naught, and then you get the operating line done, and then you can calculate or determine the number of stages, and then you learn about the pack tower, a little bit pressure drop and no calculation. We have done no calculation, but you can see an example of an example that's covered in the book, and you can check it out, okay, in your textbook. And then we continue with the calculation of the height of a pack tower. Okay, so there are many types of lines, many types of operating lines and equilibrium lines, many types of cases, and it all depends on how the lines look like. Then only you know which equation to use, right? And then you go into the calculation of Z, okay, according to example 10.64. Okay, I hope you're not confused yet at this point. And then we continue with the height and number of transfer unit. some theories in that, and then I would like to continue with the only one more thing, which is the height and number of transfer units, where you use those to calculate. Oh, sorry. Oh, what is that? So tak boleh conteng kalau tak play. Okay, so the last part of this is, before we end the class, okay, the last part of this is for you to calculate the height of equivalent HETP. Okay, HETP is related to HOG by this equation. Okay, you calculate the HETP, height of a theoretical plate. Okay, you calculate it by using this equation, and once you get the height of the tower, or you can also do it the other way around. You can calculate the height of the tower when you know the value of your n and you know the value of your HETP. Okay, so this HETP is using the HOG that you get, okay, and the n is used using the previous equation. Okay, whatever n you get. Mana tadi? Oh, sorry, my laptop pun dah penat juga. Dia pun dah mogok. Okay, so let's see. Dia dah sampai belakang sini dah. Right, so let's see the n. Nanti saya escape lah. So if you see here, okay, once you calculated the n, then you can calculate it, the HOG, and then you can, oh my. You can calculate the Z as well. Tak apa, I will cover this again in our next class to refresh your memory. Okay, because I know you're quite already saturated today. And we'll continue a little bit with this. How many slides do we have altogether? It's actually 53 slides. We finished at which slide today? We finished at these slides. Okay, 46. So quite a lot more that we have to cover, and I don't think you can grab this anymore. Okay, so we will continue on this, and what I want you to do during the weekend, you just look at the example and you do your own graph and plot and solve for B and C. Okay, and then you submit that by Sunday. Okay, so today is Thursday. Submit all that by Sunday. All right. Any question? Any question before we go?
Doctor. For the test one is week 9. Which date?
What question?
For test one, when is our test one? Week 9.
Week 9, but I don't know exact date yet. But it will be coordinated and at once. All sections are gonna do it at once. The same question.
Okay.
Okay, it's in week 9. Any more question before we go? No? No question? Tak ada dah? Okay. So hope you can grab all that is taught today. So just try to do the example of yang tadi tu 6.4 ya. Example 10.64. Okay. And submit in the e-learning. I will upload the link in a while for you to understand it further, okay? and then at the end of Sunday's class, I will give you some what do you call it? Some more exercises for you to do. Okay. All right, so that's all for today. If you have no other questions, we'll end the class here. And have a nice weekend. I know it's been hard for you guys because you have to do all this online, and sometimes tak ada jiwa kan nak belajar kan because it's online. But you are under an engineering program, which involves lots of calculations, and it's really very difficult for you to grab sometimes being far away from me, and I cannot interact with you more effectively. So let's hope that this will end sometimes and we can be in the normal class. Okay, so everyone have a nice day ahead and have a nice weekend, and I'll see you on Sunday. Bye.
Thank you, Doctor. Terima kasih, Doktor.